Okay, group, today we're going to be looking at gravimetric stoichiometry. Calculating masses of reactants and products is probably the way that you'll remember it, but gravimetric stoichiometry, working with masses. And let's start out with a little video here to show a chemical reaction which is a little hard to do in the lab, but under controlled conditions with maybe a good fume hood or outside, this would be possible. Have a look.
There it goes.
Oh, here we go.
Woo! For the record, that is a green flame. Woo!
All right, so what chemical reaction was that? Well, it was the synthesis reaction of zinc and sulfur. It's octasulfur, yellow solid combined with metallic zinc forms in a spectacular fashion the ionic compound zinc sulfide. It's very exothermic, gives off energy. The balanced chemical reaction, which represents that process, is shown here. The mole ratio, which we've been using already, can be discussed at this point now. We can look at the mole ratio between zinc and sulfur would be 8 to 1. So number of moles of zinc for every mole of octasulfur is 8 to 1. More importantly, the number of moles of zinc to the number of moles of zinc sulfide is 1 to 1, which means that for every mole of zinc, we get 1 mole of zinc sulfide. Not gram to gram, but mole to mole. Now, gravimetric stoichiometry. Stoichiometry relates to masses of or amounts of reactants and products in a chemical reaction. Gravimetric just refers to quantitative relationships using a mass. There are other possible relationships which we could use, such as volume, such as pressure, such as concentration, maybe density. These are all quantitative relationships, but we're going to be using mass. That doesn't necessarily mean that the chemical reaction involves only solids, but we do at some point need to know how much in grams. Gravimetric stoichiometry really involves all the formulas which we've looked at so far. We need to begin with the balanced chemical equation. We need to begin with the measured mass of a reactant or product, and at some point we would probably need to also know which of the two reactants or more are the limiting reagent and the excess reagent. So if we look at this process of gravimetric stoichiometry as it would be applied to the reaction of So if we look at the process of gravimetric stoichiometry applied to that reaction of zinc sulfide production, here's what we would start with. Suppose we have 1 gram of zinc and we have an excess of octasulfur. We would know that what's most important is determining not a mass ratio, but a molar ratio in order to determine the grams of the product. So we start with the mass of the limiting reagent, and we're going to convert that mass in step 1 into moles using the formula number of moles equals mass divided by molar mass. So that requires a formula that we've seen before. It requires the molar mass of our compound. This is not considering the mole ratio. This is just looking at how heavy 1 mole of zinc is. From there, step 2 is relating the amount of reactant to the amount of product based on this 8 to 8 or 1 to 1 molar ratio. So because we have an equal number of production units for the number of reactant units, in theory, if all of the limiting reagent is used up, we should get the same amount of product. And so this is going to be using the number of moles of zinc sulfide being equal to the number of moles of zinc. So that's a mole ratio. So second step doesn't involve a calculation as much as just a comparison of amounts. There would be a calculation involved, but no formula is involved. In step 3, we're converting moles back into grams. In this case, we're going to be using our formula mass equals number of moles multiplied by the molar mass. Again, here, the molar masses that we're going to be using for this would be the molar mass of zinc sulfide, and over here, what we'd be using is the molar mass of zinc. So octasulfur is not involved in this chemical reaction because it is the excess reagent. And we would need to know that in advance in order to perform this gravimetric stoichiometry method. All right, now without doing the calculations, that's the overall method. It really doesn't involve anything new, just involves putting together some concepts, mole ratio, limiting and excess reagent, with the molar calculations part of this unit so far. Let's look at another example. If we had the product mass known, and we're trying to determine what mass of reactant we start with, that is also gravimetric stoichiometry. It's relating product and reactant masses in a chemical reaction. So we start with a balanced reaction equation. Iron 3 oxide combines with carbon monoxide to form elemental iron, also solid, and another gas, carbon dioxide. Mole ratios here are shown by the balanced reaction equation coefficients. So it's 1 to 3 to 2 to 3. And any two chemicals we can relate using a mole ratio as well. In this case, we're going to relate the number of moles of iron to the number of moles of iron 3 oxide. So we start out with our mass of iron, and this would require, again, calculating the number of moles, taking that mass that we have, dividing by the molar mass of iron. From there, in step 2, we're going to be looking at the mole ratio between those two chemicals, which in this case, the number of moles of iron 3 oxide is equal to half the number of moles of iron. So we divide 1.790 by 2, or multiply it by half. Now we have, again in theory, that 100 grams must have come from half as many moles of iron 3 oxide. Now we're going to convert our moles back into a mass using this relationship here, which completes the process. So gravimetric stoichiometry always starts with a calculation involving moles, a mole ratio, and then it always finishes with a calculation involving mass every single time. So it's very consistent, and again, just putting together all the concepts that we've looked at so far. So look at one more example here, and then we'll try to set up our flow chart for some more. So in this case, this is the combustion reaction of butane, a hydrocarbon. In this case, we're trying to determine not just a mass, but the number of molecules. So here, we could start with a known mass of our limiting reagent. We'll assume that oxygen is excess, which is good. We always want oxygen to be excess, so we produce the most common oxides of carbon and hydrogen, being water and CO2. We begin with our given mass. From there, we can calculate the number of moles from that, knowing the molar mass of butane. The molar ratio that is necessary here is a 8 to 2, so the number of moles of carbon dioxide is exactly equal to 4 times the number of moles of butane. And then from there, we can convert that into a mass, in this case, or a number of molecules. Now, gravimetric stoichiometry could also involve calculating number of particles. So here we would be looking at number of particles equals number of moles multiplied by Avogadro's constant. So that's a sort of a variation of gravimetric stoichiometry. We could determine how many particles are produced or how many particles were required in the reaction. All right, in our summary note here, then we have 3 basic steps involved. Converting a mass into an amount in moles, using a mole ratio to predict an amount of moles of a desired substance, could be a reactant, could be a product. And the last step would involve converting that amount of moles back into a mass or possibly number of particles, as was shown in the last example. Visually, this is nice to see, and I would encourage some of you to use this kind of flowchart method, and you're going to have an opportunity to do that in your groups in class tomorrow. Whenever you set up a balanced reaction equation, feel free to communicate as much as possible, show what you're doing, direct your steps using some arrows, and make it really predictable. The arrows may move in the opposite direction if we're starting with product information, but the direction is independent of the steps involved. We're still going to begin with the mass, then to moles, then back to mass, or possibly particles. Okay, here is student worksheet 5.4a, practice questions on gravimetric stoichiometry. There is not enough room to solve these questions, and you'll often find that to be the case. However, we can at least provide the framework for the solution, which is the balanced reaction equation and the flow chart or the steps involved, and you'll have a chance to work on that method in class, as I mentioned before. So for this first example, we have to convert words into a chemical reaction equation. So let's start with iron 3 oxide. We know that is Fe2O3. It is rust, so it's a solid produced. Oops, that's maybe needing to be changed to the other side. Fe2O3 produced by, this is a synthesis reaction, iron with oxygen. So we have solid iron combining with gaseous oxygen diatomic, and we begin with 500 grams. So what I would do is under each chemical formula, I write the information that I know. So 500 grams is a mass, so we're going to convert that mass into moles of iron. We're going to convert that into moles of Fe2O3, iron 3 oxide, and we're going to convert that back into a mass of Fe2O3. So that's the skeleton reaction equation and the framework for the steps involved. I'm going to balance this. I have two elements, so I'll balance iron first, and I have, actually looking at this, I think what I'll do is I will balance oxygen first because I've got that odd even problem again. So I'm going to make 6 atoms of oxygen on the left side, 6 ions of oxygen on the right side. That makes 4 here. So I'm going to fill in the information that I need to know. I would need to know the molar mass of iron, but again, I can calculate that molar mass of iron above the second arrow. So this is step 1. Step 2 is applying the mole ratio, which would be number of moles of my product is half the number of moles of my reactant of interest, and then the last step would be converting moles into mass, which is multiplying the number of moles from step 2 by the molar mass of iron 3 oxide. And that will be it. Calculations need to follow significant digits, so that's the only other thing I have to consider in my solution. Okay, looking at number 2 here, we have this type of reaction. Looks like we've got silver nitrate as a reactant and sodium sulfide. So it looks to me like double displacement. And that's one of those skills that you're going to need to carry over from chapter 3 on chemical reactions, is recognizing what are the possible products, because they're not mentioned here. So we're going to go right to the chemical equation in skeleton form. So we have silver nitrate, which is AgNO3 in solution. So that's aqueous, combining that with sodium sulfide, which is Na2S, not sulfate, but sulfide. So a binary ionic compound. In a double displacement reaction here, we could get silver sulfide and sodium nitrate. We should have enough experience at this point to know that all nitrates are soluble, highly soluble, so we have an aqueous product there. So sodium and nitrate are our spectator ions. Silver and sulfide are going to be the reactants that are actually going to form. I believe silver is 1 plus and sulfide is 2 negative, I know, so I'm going to give chemical formula correctly there. that would definitely affect the molar mass. You have to make those connections, and I believe that's a low solubility product. So that would form a precipitate. We can balance that chemical reaction equation. We have two sodiums on the left, so let's balance sodium on the right side. Now that produces two nitrates. Let's balance polyatomics as a group. Going back to the left side, two nitrates there. That introduces two silver ions, which balances for silver, and sulfur is already balanced. So that is our balance reaction equation. From there, we are given the mass of silver nitrate, which is 2.00 grams. So let's go to underneath that compound, write the information we know, and that's all we know. So we want to know the mass of precipitate that should form. So that's our precipitate. So identify that. And now let's go and apply gravimetric stoichiometry. So the first step is going to be going from mass to moles of silver nitrate. From there, we need to cross over to the product side. And in the step 2, you can sort of thinking as a crossing over, right? We're going to be going from the reactant side. The mole ratio is what allows us to cross over to the product side. So that would be a mole ratio of moles of silver sulfide, in this case, is half the number of moles of AgNO3. So that's just how this chemical reaction works, is that silver sulfide has twice as many silver ions as silver nitrate. So when we look at the number of units, it's a 2-to-1 ratio. So moles of product is half. From that point, we can calculate up to our product in mass, which would be our answer. And again, filling in for steps here, that's our third step. That's going to require number of moles times mass of silver sulfide, and this would require us to get moles from mass of silver nitrate and the molar mass of silver nitrate. Moving on to number 3, determine the mass of water vapor formed when 1.00 grams of butane is burned in a lighter. So in this case, we have butane, hydrocarbons, C4H10. We've done this one already in a previous example here. So let's just not double up on extra steps. From this flow chart, we have already all the steps that we need to follow, except in the end, we're not calculating the number of molecules, we're calculating the number of grams. So number 3 here would be identical to the previous example, except following the traditional mass to moles to moles to mass. Okay, so I'm not going to do number 3. So see previous slide. Okay, for flowchart. Okay, number 4, last one here before we sign off. Your assigned work, as you can see there, there's a good variety of different things that you're working on. In groups, you're going to be working on balancing chemical equations, giving a flowchart for some questions 1 to 6, solving and submitting 9 or 10, page 228 in your group, independently working on 1 to 4. And then there's an optional bonus thinking inquiry communication assessment, which is lab exercise 5.4.1. If you choose to do that and submit it, I will add it to your thinking inquiry communication mark record for the semester, and that will hopefully increase your term mark for that category, or those two categories. Let's look at number 4 to close off. Your silver metal can be recovered from waste silver nitrate solutions by reaction with copper metal. Now if you read it carefully here, the reaction with is silver nitrate and copper. It's not silver reacting with copper. So this should be recognized as a single displacement reaction. Silver is recovered, so that's a product. So silver is an element in a solid form, and there'll be 2 possible products here. We're going to get silver, and then starting with silver nitrate, AgNO3 solution, aqueous, and we're combining that with copper metal, solid. We're going to get copper nitrate. Copper 2 nitrate in this case would be the most common nitrate formed, so CuNO3 2, and that's aqueous. As we know, all nitrates are aqueous. So let's balance this. We have two nitrates on the left side, two silver atoms on the right side, and copper is balanced as an element. So from here, we can write what we know. We have 50 grams of copper. So in this case, 50 grams of copper is given. Now, because the silver nitrate is the waste solution, here's an example where you don't know how much silver nitrate is present. So quantitative analysis would apply here. 50 grams is whatever, it's an amount to start with. That may not be excess. You would know if you have completely reacted all of your copper metal and you have no metal left, you would add more. But we can at least determine how much silver can be extracted using that 50 gram amount, knowing that silver nitrate and, or rather silver as an element and copper as an element are related as a 1 to 2 mole ratio. We can from this go to moles of copper, moles of silver, mass of silver. So this is simple stoichiometry method. Step 1, step 2, step 3, and label these here with formulas. We have moles of copper would be the mass, 50 grams divided by the molar mass of copper, which would just be its relative atomic mass from the periodic table. Step 2 is a mole ratio. Moles of silver, in this is a 1 to 2 ratio, so we'll form twice as many moles of silver from the limiting reagent copper. So if all of that 50 grams is used up, then we have to use the chemical which is completely consumed. It's a little bit like doing baking in the kitchen. If you completely use up your flour, you can determine how much, whatever, how many batches of cookies we can make. If you have a whole bunch of oil left over, you can't use the amount of oil that you started with. You'd have to know exactly the amount that was used up. So let's finish this off here. So 2 to 1, once we know the number of moles of copper, we'll double it to get the number of moles of silver that can be formed from this reaction. And then we can take the last step, which would just be calculating the mass, and that would be number of moles times the molar mass. Again, there we're looking at silver is an element, so the relative atomic mass for silver from the periodic table would close off that solution. So tomorrow in class we're just working on, as I said, some group work, some independent work, and this will take a couple days in class. So you will have time to work on this, and this is a really key section in the textbook. I mean, introducing the mole was really important, but working with stoichiometry is important. Once you understand stoichiometry and you can apply this method, you can apply it to anything, whether the chemical reactions are taking place using volumes. We'll have volume equations later on. Maybe they're taking place in using gases. We'll have equations that relate moles for gas reactants and products. Stoichiometry is really key concept in chemistry, and if you're going on and taking grade 12 chemistry next year or next semester, this will be really important for you to be able to master. So have lots of questions and we'll work on them in class tomorrow. Take care.